Testing sound. Testing sound. Test. Okay, great. We're good. Sweet. Let's get to it. So last time, whoops, that's not what you're meant to be able to see. Why is it showing that window? There we go. Okay. So last time we were working on the following. Hello everybody. So we have been working on Glyphos, which is my app to do math, and not just calculations, but math of the sort that you would do in middle school or high school or college, or at professional as a mathematician, or economist, physicist, actuary. All these things. This is where I've lived my life. I have a math background. I was an actuary for a while, and then I was a software engineer. And my feeling is we should have a math processor in the same way that we have word processors. We can do our writing on a computer, and it's faster than doing it on a typewriter or by hand. And in the same way, our math should be easy and ergonomic and error-free, or at least error-reduced if we do it on a computer. So Glyphos. And the basic idea is, I can, let's show the app if I can. Just very quickly. Uh-oh, what have I done? Does that work? So this is the front end, and my function key is in a different place on my keyboard than I'm used to. And what's showing up now? Not the right thing. Fighting with OBS a little bit. Why? It's because these things are the same window type, presumably. Order, that doesn't do it. Window, VS Code window. Properties, window. Okay. This, and then let's copy and say Glyphos, and this is this. There we go. And sorry, I have to fix my setup here to be able to show everything I want to be able to show. Let's duplicate this, and let's say Glyphos. Okay, so now when I push this, it goes to my front end code. Nope, sure doesn't. Interesting. Why not? Okay, there's my front end code. And now this has changed. Why? Because why are these bound together? I'm gonna stop fighting with OBS in just a moment. It's because these sources are somehow shared by reference, right? That's the problem. So if I get rid of this source, remove, yes, I'm sure, and then I copy this, why can't I copy it? Can't copy it. I don't know why. All right, whatever. For now, this is fine. Okay. So anyway, this is the app. The app is a basic text editor. I'm a text editor. It's the front end right now is just a VS Code extension. Eventually, this will be browser-based and all sorts of good stuff like that, but for now, it's a VS Code extension. And and you type whatever you want, all the good stuff is over here on the left. So there's a type system that's entirely defined by the user, but it's importable and shareable. So in particular, we could have a type called real numbers that has some real numbers and also some operations on real numbers, and another type called proposition that right now just has equals, but you can imagine this having, P's and Q's for propositions, and or some logical operations. All of that is easily addable. Generated types I'm going to skip over. Interpretations are again user defined, but also shareable and importable, and they tell Glyphos how to interpret something like this. So when it sees times, it's going to go here and it's going to say, oh, it matches the multiplication, and it's an infix, meaning that it operates on the two things outside of it. It's inside the two things it operates on. It's got precedence, which handles order of operations, and it outputs to this type multiplication, which we saw was a real number, a subtype of the real numbers. Blah, blah, blah. Interpretations let you parse stuff. Statements let you say, here's a thing that's true that I'm going to do some transformations on. So I don't remember. I guess I was doing something with FOIL last time I was using this. I'm going to remove all the statements for now. And then transformations are rules that you're allowed to use to transform statements that are true or false. So for instance, x plus 0, you can turn into x. Commutativity is in here somewhere. Associativity of multiplication, x times y times z, can be mapped to x times y times z. And the goal today is going to be to continue building out optimization. Basically, my belief is that the way that these statements are stored right now, statements and transformations, which is as a tree of symbols, is resulting in a bunch of performance slowdown, basically because all of the operations that I'm doing on it are kind of recursive, and it has to follow a bunch of pointers, so we are instead going to encode them as binary. And we'll start working on that in a moment. Just to show a brief example of what we can do, I was reading something on Reddit earlier today that was saying, it was somebody asking, let's see, what were they asking? Let's get rid of all this. I don't think I need it right now. So there was a Reddit question. It was, I have $2 million. Can I draw 100K from it without dipping into capital? If not, what would how much would I need? That was the Reddit question. So, and there were lots of answers, and it's like, by the way, we care about inflation. So let's assume 3% inflation. Then what return, and really it'd be risk-free return, do we need? And you can get into, there's a whole Reddit thread back and forth on like exactly how to frame this question. I'm gonna ignore all that and just focus on the meat of the question at the moment, which is we need some kind of return. We need, what do we need? Basically just need this to equal 100K. Need this to be 2 million. We need some kind of rate of return. Is how much you're going to draw every year, but it's also going to go up by inflation, but that's fine because we can just subtract the inflation rate off of it. So this is going to be 0.03. Right, so each year inflation is going to take away 3%. That's not actually quite right. Okay, so each year you would have okay, amount at time 0 is 2 million. Amount at time 1 is 2 million times divided by 1.03, because we lose 3% to inflation, times whatever we earn to the first power minus whatever we draw down, which is 100K. And so the question is, what does R need to be for this to get us back to 2 million? Yeah, there we go. That's what we need. Okay, so this is 2 million again. And so let's just write in terms of millions. So 2 million, 2 million, and then 0.1 million. And this is the thing we need to solve. Yeah? So let's hypothesize this, which throws it into the statements. over there on the left. And notice, by the way, it gets all the nice parentheses and everything, and we can double check we agree with these parentheses, but we do. Division and multiplication got their parentheses before minus did. That's great. I think I want to remove that green highlighting or make it better, because right now it doesn't handle the case where the parentheses are different than what's in the actual statements, which is a little awkward from the UI perspective. Also, it's a little ugly. Okay, so now let's see if we can do this. So we can we should be able to say 2 plus 0.1, and I'm just wondering why this says 0.1000. I wonder if that matters. It's being parsed as a real number, so that's correct. I guess it's fine. I hadn't thought about that before. I wonder if... Should be fine. We can always evaluate it. But I guess that means we need to make our parentheses correct over there. And then let's just copy this. Plus 0.100, and then plus 0.100. And whoops. And let's try to derive that. Doesn't like it. Let's put parentheses down. Still doesn't like it. Why not? So we should have some rules about equality in here. Namely, if I can say anything about some object, and I know that that object is equal to another object S, then I can say whatever I said about the object about S. Is that what's going on here? Adding to both sides. So let's see here. The statement would be 2 plus, or it'd be like O plus 0.100. Yeah, so I feel like that should work. Because this is equal to this. And so what's wrong with what we're saying? Wait, what is going on? Something weird is happening. Oh. This shouldn't matter, though. Why can't I evaluate 2 divided by 1.03? 1.03 is real, 2 is real. If I evaluate it, it comes up with the right answer. that worked. So I was able to evaluate the division. And so then why can't I say this? This is a statement about an object. This is the same statement about an object on the other side of an equal sign. Okay, it's because I don't know this part. This part isn't a statement. Is the issue. Got it. So I only I have that O equals S here. I have that this equality holds, but I don't have that this side is a statement because it's not. I've done this before though, where I've added to both sides. Feels like I should be able to do that. This is not what I was planning on doing today, but so proposition any O, or yeah, any real equals any real S or whatever, X and Y, I guess, since they're reals. This should imply any real X plus Z equals any real Y plus Z. Okay, how do we prove this? Well, it's because I can say Z equals Z, and then I can say any real X plus Do I need another law for this? I don't feel like I should. I feel like I have some tests to test things like this. I'm not going to be able to tell what they are, though. Because they're integration tests. Can I not prove it with this? Feels like I should be able to. Have any real X plus z minus z equals any real y. I have that for sure. I don't think that helps me though. Let's see, do I have a test for this? For a test. Oh, my tests are possibly failing. It's okay. Yeah, my tests are failing. And on both sides. There we go. Adds to both sides. Okay. So what did I do here? Yeah, I used a slightly different form of Leibniz lemma. So instead of saying if I have a statement about something and that something equals something else, I can say the statement about something else. I use this form where it's just if x equals y, then I can say anything I want about the two of them. And I thought I could prove this. Is that what I want to be able to say? Proposition x equals y implies any x equals any y. Is there any way I can say this? So if I have x equals y, that's a statement about x. So if I said universal any O is x equals y as a function of x, and I said O equals s, x equals y, where O, x, and s is y, then I have universal any of y is provable from that. Which is y equals y. That doesn't matter. That's true, but it doesn't matter. Maybe I can't prove this. Maybe I need another law. I wonder if I'm missing something. Let's see if ChatGPT has any ideas. X equals y. seeing if I'm missing anything that ChatGPT knows better than I do. Okay, from the rule x equals y and p, infer that if px is true, then py must also be true. Okay, so let's see. This is, oh boy. Sorry, I was showing the wrong window there for a bit. Oh my god, ChatGPT, copy in a way that doesn't make me angry. What is happening? Okay, let's not do that. Can I get this in a saner way? A little bit. Okay. Can I turn on wrapping? There we go. This is still unreadable. Okay, so it's saying assume x equals y. So its proof is assume x equals y. And then case if px is true, then py is true, which is definitely true. And then the other case is if py is true, then px is true, which is certainly the case. Therefore, px is equivalent to py. I mean, we could say it's more like this, right? It's more like not px implies not py. And so they're equivalent. And so they're equal, is what ChatGPT wants to say. That doesn't feel like it's an actual proof, though. There's nothing that says that something that's biconditional, like something that's equivalent, is equal. So I think we just need the other law also, which is, all right, so let's just add it. We're gonna add a transformation. It's gonna be that if O equals S, then universal any O equals universal any S. Okay, and now this should be true. There we go. Okay. Pretty sure we just need the separate axiom for that. Okay, and so let's double this up and evaluate things. derive that. And now let's rearrange some parentheses. So we want so it's not quite gonna like this because we're not gonna have associativity of subtraction defined. And this is part of the reason why we want to do the optimization we're doing is to search, so we'd really like to just move these parentheses like such. Right, this should just be true, but it can't be derived because we have to move some stuff around. So let's go in here and let's say plus negative that. Should be derivable. And now, is this going to be derivable? Yes, it is. Okay. And now 2.1. So now this part just goes away. Oh no, it doesn't just go away, it goes to +0. Okay, things are getting a little bit slow. What's the problem? Surely I can write... Surely I can write this. Do we have a law to this effect? We want that negative x. Okay, I imagine the problem is that we only have the flipped version. So we have x plus negative x goes to 0. But we don't have the inverse of that. Fair enough. So again, this is a case where like two pretty trivial transforms could be put together to get us an answer, but they're not, because right now things aren't fast enough to scan deeper in the tree than one step. Okay, so that derives, and now this should derive. Albeit quite slowly. And now we can say this. And then we can say this. Did not like that. What's the last statement we got? 1 plus r. Okay, we need the distributed one. Okay, let's help it be a little faster by saying the only one I care about is this one. No. I wish these would. I need to get these to order nicely. It's this one, but only not the statement and scope, and we want distributivity. Okay, and that should make this go. Can't do it. Why not? That. X times y plus z. Sure, looks like what that looks like. So what's the problem? What am I missing? The type's all correct? No, R is garbage. Oh no, R wasn't parsed right from the beginning. Yeah, this is another thing I want to add as a feature. Let's write that down. So right now, it's possible to parse something that doesn't have an interpretation, and it just gets jammed in as an object. And that makes it really easy to go a long way and then realize that in fact you don't have a good interpretation. So let's add an interpretation, and let's put everything back in scope. Error on parsing if there's no interpretation. Okay, so here we go again. Hypothesize this, derive this, derive this, derive this, derive this. Just keep on deriving. A little slow. Keep driving. Yeah, so the main slowdown here is coming from just needing to check. You know, we're getting more and more statements. We have whatever 8-9 statements right now, and then a lot of transformations, and it's got to check that all of them are legit. Like, or it has to look at all the pairs, roughly speaking. There's some optimization, but it's trying to look at all the pairs of transformations and statements and see if it can derive, and that's just going to get slower and slower. There are some optimizations in there, but a big part of it is that it's having to chase down a pretty recursive tree every time it wants to do anything. And so the goal of the optimization I'm working on right now, and that I'll get back to soon, even though I've been doing this for an hour, is to make those a lot faster. Okay, so now we should be good. By the way, let's double check that R now has a proper type. Yeah, R is real, good. So we made it all the way down here. Is that true? Maybe. 1 times R. And then, yeah, here. So let's... Hello, computer. Give me control, please. What is happening? I'm confused. VS Code. Why? Why can I not type? I would like to type, please. this is not my fault. This is VS Code being weird. There we go. Okay, so this is fine. And now we're gonna evaluate this. And go ahead and drive it. And then, so here's a question. Now can I do this? Minus that and add it to the left. I think I should be able to. Maybe. Nope. Why not? Let's take everything away from the scope except we need X to Y. We need this one. And we need the fully distributed and evaluated one, which is this one. Can't do it. Interesting. Why not? Parentheses, probably. No? Yeah, it did. Okay. Again, like this is the current ergonomic issue is everything's too slow to be able to work out that applying associativity and then this transformation would have been sufficient to derive it. Wait, also, is this right? Okay, it got the parentheses right. Let's do it this way. So now, again, we can evaluate. Oh, it doesn't do anything, though. We can reverse this side. We need our transformations back in scope. Not getting there. Let's only put commutativity in scope. And then do it. Oh, it derived it. It got there eventually. Okay. And now this. Why? this one. And okay, now we can evaluate. Now why can't we derive this? Because we need our transformations back in scope. Yeah, so this feels awful. Anyway, maybe I should stop doing this, but you see the picture. Now we would rearrange the parentheses over here, we would cancel these two, and then we would divide both sides, and we would keep playing this game, and we would get there eventually. The issue, of course, is that this has been extremely slow and laborious to do, and all of that is because it's not fast enough for me to have some sort of search happening where it can search through multiple possible moves, multiple possible transformations in a row. I have to apply each one directly, and because the size of this explodes, it ends up being really slow to compare those two. So what does that mean for what's the optimization that we're working on? What we're working on is goal. Make derivations faster in order to allow us to automatically find 2 to 3 step derivations. In particular, so we'll say like belief, a lot of the slowdown comes from needing to do recursive operations like replacing x with y in some SymbolNode solution, rather than using a pointer-based tree structure for SymbolNode. Use a binary encoding that's flat and permits fast operations. Okay. And so what does, let's go look at our nodes. So what does that look like? Well, the goal was to have something like, if we had a plus b equals c, we would do something where we tracked the parentheses, like this. So opening and closing parentheses would get ones, and then we would say, so we'd say like parens is this, a is this, b is this, etc. The issue I'm running into is, I think I did some work on this offline, and I think this representation of parentheses, well, I should say the point is that binary numbers are really cheap and efficient to store. Right now I'm using arbitrarily sized binary numbers, which are going to go on the stack rather than the heap, so that'll be a little slower, but hopefully still faster. There's a world where eventually we store 64-bit ones on the heap. Anyway, like if this representation is 64 bits or smaller, we use heap allocated storage. Pretty sure that should be possible, but we'll optimize that if we need to. But I think we have a bit of a problem here because I think it's possible for this representation to be ambiguous, in the sense that if I want to ask for, and actually this isn't even how it would be represented. It would be represented like this. Like this. So this would be 0101 001 01. This would be 00001 0000, and this would be 000000100. The problem is I don't think I actually know. I don't think I can unambiguously figure out, and there'd be C equals something and equals something and plus equals something. I don't think I can unambiguously figure out where the parentheses are here, is the problem. I know where they are, but I don't know if it's a left paren or a right paren. Maybe I should just have left parens and right parens, though. It's probably the way. That's a easier solution, actually, than what I was about to do. I think that's better. Okay, so let's come up here. And where are we? Binary symbol tree. We're going to call this left parens. We're going to call this right parens. We're going to get left parens, right parens. We're gonna rename this length parens and trees. We're gonna go right parens. Okay, so to do optimize SymbolNode to binary tree. Separate out left and right parens is what we're working on now. Okay. Partial order for binary symbol tree. We'll figure out. This is not what we're doing. We're doing left parens. We're doing right parens. We're doing right parens. Left parens. Right parens. We're not doing this. We're not doing this. Okay, so how are we validating that things are correct? Left parens. Let's assert equal left parens dot bits and right parens dot bits. Let's assert equal left parens dot count ones, right parens dot count ones. This will be left parens plus right parens. Okay, the point here is that all, because there's a character somewhere, then at the end of the day, if we sum up our left parens, our right parens, so this is now going to be left parens will be 0, 1, 0, 1, 0, 0, 0, 0, 0, and this will be 1, 1. Can't add. I'll do this. Yeah. No. No, I guess not. Okay. Do this though? No, this. It's a little awkward, but what to do? Okay. It needs variable length. No. So this should be true. But also hang on a second. I'm realizing this actually won't always be true. Length is always left parens dot bits plus 1, because if it's an empty but it's not going to matter. The problem is that bits returns based on, if there's a bunch of leading zeros, bits doesn't know whether those are actually a bunch of zero, like how many zeros are in front. And for left parens, we know that there's exactly 1 0 in front because there's always an object in front of any parens, even if there are no parens. But we can't actually confirm that with the other ones. That's okay though. Okay, I think this is fine. Get root shouldn't matter. Shouldn't matter. Okay. Cool. Get matching right parenthesis is gonna matter. Left parens. Do the same thing with right parens. Parens, get matching right parenthesis. So this is going to be match self dot left parens dot get bit from left self dot length in bits index none. We're gonna return none. Can we just do it this way? Can we just say this dot map No, let's be explicit. Match this. None. Not a valid index. Let's warn in that case. Get matching, right? Parenthesis called with invalid index. None. Some true. No, some false. Let's handle first. Warn. Get matching, right? Parenthesis called on none left parenthesis. Turn none. And then if it's true, then what do? We say let's see here. Let mute I be index plus 1 while let some I equal self dot get let's just say while actually we can just say for I in index plus 1 through self dot length in bits. Let level let mute level 1 if is left paren I level plus equals 1. Else if is right paren I, then if level is 0, minus equals 1, if level is 0, return sum I. Warn no matching, right, parenthesis, bound, and return none. I'm a little concerned that these fail. They don't fail silently, but they just warn. But I think we're gonna live with that for now. Okay. Get bit from left. I think rather than doing this, what we'll do is left paren. Else warn get match matching right parenthesis called on non-left parenthesis. Okay. Expected semicolon. Okay. Let's rewrite this as is left paren. And we'll do the same thing, but for is right paren. Okay, and now is left paren equals sum true. Why is this a reference? There's no reason that should be a reference. Okay. All right. Get length parens and trees. Going to return two binary encodings now. Children left parens. Children right parens. This needs to have left and right, and then this will be left, and this will be right. And this will be left parens. Okay, so left parens is going to start with 0. And this will be false. And then right parens. Oh my god, go away, go away. And then let me right parens is going to be what? It's always just going to be children, right parens. Concatenate 1 binary encoding 1. It's just the children with a 1 at the end. And then what's the issue with all this? Parens, and then left parens, right parens, so this is for node trees. Right parens. Okay. This doesn't have to be mutable. Okay. This is new. Arrow parsing this. Okay, yeah. And down here we want left parens. Here we want expected right parens. Left parens is 0. Right parens is 0 in this case. And then down here, this is going to be left parens. This is going to be right parens. This is going to be 0. This is going to be 0. Expected right parens. We're cruising. We are cruising. This is going to be left parens. This is going to be right parens. And this is going to be 0, 0. This is going to be 0, 0. Okay. And here, expected right parens. Okay. And we're looking decent. Let's see what happens if we do this. Okay. Okay, let's look for structure everywhere. Get child. So this is going to be is left paren. Children length parens. Oops. Okay. Hey, looks like we compile. So there's another potential optimization here, where if the tree is fewer than 64 bits, like if it has fewer than 64 characters, including parentheses, then we can allocate it to the heap, maybe. Okay, test failed. Get our tests to pass is the next goal. Okay. 1859. So we're differing here. Yeah, sure. So left parens should be this, and then right parens should be this. Gotta say, I really hope this optimization helps, because it's taking a bunch of time, and I'm like 80% confident that it's gonna help. But it's a little dicey. Ooh, get matching parenthesis called on a not left parenthesis isn't great. Gonna have to check that out. What's this? Panicked at 1872. What? There we go. Okay. Okay, so get child isn't working, and we're getting some warnings. Go look at get child. So get child 0. Is the goal. So it has no children. Just says, do we have no left parentheses? So that's got to be passing. This has to be passing. Don't really think this is doing very much now. So we're gonna look. So we're going to look at the place just after the left parenthesis. Okay, we're going to intentionally check if there's a matching right parenthesis. If there is, if there's not, then we just kick the don't we just so we're walking through trying to get the nth child, the indexed child. Just gonna call this n. Okay, so then the right parenthesis, there is no right parenthesis, then it's just in the same place. If there is a right parenthesis, then that's where it is. Then we set it to +1. And so then the child index fine. Is at the location of the okay, so this is passing in the left hand index. Let's say starting at wait, why is this returning none? So we say subtree start. And if it's a left parenthesis, this isn't right. So there are three cases. There's the case where it's a function. So it's like match self.get matching right parenthesis subtree start. If it's some index, some r_n index, then I'm going to say let subtree start, subtree end be this. Then index +1 r_n index -1. If none, then match self.get matching right parenthesis, or maybe just match self.is left paren index +1 some true. Let's actually say none or some false. Okay, some true. Then we're going to do something none. Then we're going to return index because that just means that it's a constant. So this is going to be we were appointed at a l_paren include everything, return what's inside. That is the point here. The point here is we were appointed at a singleton, and we were appointed at a function. So in this case, we do index r_n, no, index, yeah, let's just do get matching right parenthesis, and then here this will be some r_n index r_n index, yeah. And now, I don't know why I'm doing that. So now left paren don't know why I'm doing that. Okay, let's see if that's better. I think it's probably worth testing this function directly, which is what I'm going to do. Still failed. 568. Interesting. put backtrace on and rerun it. Gets children, get child, subtree starting at 246. So how can this ever be too far? Which statement's failing? Get child 2. Because there is no second child. Okay. So so if index is greater than or equal to self.length, return none. Okay. Still failing. 571 now, though. That sounds like a different number. Oh, same number. Same get child call. 224. Yeah, it is. Really. Get child. Child index. That's weird, right? Test index. So we come in here. There are only 2 children. Test index equals 2. Oh, is there a right paren at the end? No. If self dot is right paren index, then warn you are pointed at a right paren. I don't think this should be the case. Oh, it is the case we were pointed at right paren. Okay, why is that? So n is 2, test index is 2. We get a matching right paren. So is get matching right parenthesis failing us? I don't think so, because we've tested it. Okay, but it's test index. We add 1 to that. Now test index is 3. We do it again. Test index, now test index is 4. Now we're looking at a right paren. Got it. Okay. Child index sum true. Return none. Sort of hate all these warnings. Feels like things should either fail or not. Still fails, but in a new place. Okay, left equals right. So they're not equal. Which one is this? 298. Equals B equals C. Let's take a look. Let's just open up a new one. Okay, well, the right hand side is way shorter than the left hand side. There's something going on the left. Left, binary symbol tree. this, this. Nodes. So what's going on? A equals B equals C. We think should be A equals B and then C. Equals A and B. Left parens. Right parens. Okay. If I look, oh my god. Let's put word wrap on. We've got A and B here. And we have C. Hang on a sec, there's a third one. Left equals A, B. This one also has A and B. Let's test the children directly. So A equals B equals C. Sum A equals beta clone. And then this and this. And then this and this. Just to break it down. I'm imagining I'm going to get a failure on 1898 now. I'm imagining it's because somehow get child isn't working. 1899, so 1898 was okay, but 1899 failing on, well, it's got A and B in it. This looks like A equals B here somehow. Get child. Okay, so get child is a 1. Then we check for parens. There is a parenthesis. By the way, there's an optimization here for get children where we don't have to do this. Because this loop is what generates these, so okay, so from 0 to 1, we start, test index is at 3, this returns none, no, that's not true, this returns 4 or something. Get a right parenthesis back. We set the test index to +1. Now it's at 1. Now it should just see a C, but it doesn't. Let's check out get matching parenthesis on these. A equals B equals C. So this is going to look like equals equals A, B, C. So then L paren should be 0, 1, 0, 1, 0, 0, 0, 0, 0. R paren should be this. So 0, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8. 8. It's going to be some 6. Yeah, we want to get children to be fast too, so I think. Okay. 1913. Really? That's surprising. So get matching parenthesis is working fine, but get child isn't. So in our example, equals A, B, C. So when we're at 0, test index is 2. That's an equals. Right. Got it. Okay, so this here needs to be if self.get matching right parenthesis test index +1 equal else this would be if let sum r paren equal this, we're in a function, and so we need r paren. Feeling good about this one. Hey, test pass. Okay. Okay. Now, rather than doing this, let's optimize a bit. Turn to push. And this is going to be while test index is less than self dot length in bits. Do all that. And okay, so this way, because the way we were doing it before getting each child, we were going to end up looping through the whole thing every time we were going to do a little suicide sprint. What is this? It's a problem. Turn, look, see, we really think this should always exist. Still working. Failed now, really. $19.28. Children. Left, right. Somehow I'm not getting both. We're not getting that warning, are we? No. Okay, so in this case, we're calling get children on something that's 5 long. It's like equals AA, 5 long. Test index is less than 5, so it's going to go up to 4. Our paren get matching on 2 is going to return none. We're going to check if there's a right paren. We're not. So we're going to get back 2. We're going to get a 2 plus 3. It's going to be this, right? Because this way we're going to get we're going to push everything until we get to the end. It seems right. Great. Okay, there's some copied code here. I don't love, but I think we can live with it. Okay, let's I think I had another test for binary symbol tree. Did I? Yeah, which is still passing. Okay. Cool. Oh. Get rid of that. Let's run all of our tests, because why not? That didn't actually recompile. Okay, tests are passing. These things are separated out. We'll commit that in a moment. So next up, so we need to start going through the SymbolNode. Excuse me. The SymbolNode functions and writing versions of them for binary tree. Which is fair enough. So let's encoding is more private. What's the problem? do this. Okay. Let's commit this. Initialize and get children for binary symbol tree. Okay. All right, let's look at what we need to implement. Oh, by the way, did that test... did that test that we were able to rebuild the symbol node? Did. Cool. Okay. Okay, we have a bunch of helper functions that I'm not super concerned about. Length. We're going to want to implement and contains arbitrary nodes. Okay, let's start with those. Binary symbol tree. We're going to say get and children use as self dot get children dot length. Seems fine. Contains arbitrary nodes. Is gonna be self.nodes dot iter dot any label root dot is arbitrary. Easy enough. All right, what else we got? Let's just implement SymbolNode functions for binary tree. That's what we're doing right now. Okay. Contains arbitrary node, contains substatement, and gets substatements. Fair enough. Let's see here. Get substatements. This is just going to be this should basically be the same function actually. Okay. Contain substatement. Actually, get substatements doesn't have to be recursive, right? It's better if it's not. It's just for I in 0 self dot length in bits. I need to return equals hash set new, and then it's just match self dot get subtree starting at I some subtree then to return dot insert subtree. Presumably have to clone it. None. Nothing. To return. Hash for binary SymbolNode. That wasn't a problem before. Fun times. Okay. to implement hash for binary symbol tree. It's a thing we need to do. Let's just have ChatGPT do that. Binary encoding, symbol name, symbol node, root are all already hash. Okay, do I already have hash stuff up here? Nope. This. And let's grab this. And let's throw it over here. What is happening? Okay, so this is correct. Somehow my parentheses are messed up. Error. Okay, but this doesn't seem to be a parenthesis problem. So back up here. I need these things. And then in here somewhere. I need these things. No method called hash. Binary encoding. Fine, needs to be hash. And how we doing? I assume it doesn't come through on my microphone, but my kids are jumping around upstairs. So hopefully it's not coming through. If it is, let me know, and I'll see if I can put a filter on it or something. Okay, tests are passing, everything's compiling. Good news. Great. Implementing hash is done. Okay, let's keep implementing other get substatements. I guess debatably I should probably test get substatements. Test binary SymbolNode tree gets children. What was this one? Tree from SymbolNode. Okay. I guess we'll use. Let's just add it to this one. Insert equal a equals b equals c dot get substatements is going to be backup a equals b equals c a equals b a b c. Probably should be cloning all of these. Oh, that didn't work. Okay. Okay. Okay, assuming that works. Where do we go next? Get predicates. Ooh, failed. Surprising. Failed. J is less than length. So 661. Seven. Length in bits. That certainly seems like it should be allowed. Four. 39. Subtree start, subtree end. Get subtree starting at. Okay, the more I use this, the more I don't like this warn. The other one's fine. So all we do is we ask at every spot whether there's a associated subtree. To write paren, we quit. If get matching right paren, so we have to be pointed at something in order to get here. It's an L paren. Seems fine. Get matching right parenthesis index plus 1. That's a fair question. What happens? What happens if we take a get subtree starting at 0? We should get a.clone. But I suspect we're not going to. I suspect this is going to crash because when it so we're pointed at a singleton. Maybe it's okay. It does panic at 1958. Yeah, okay. Oh, but hang on a second. This is fine. Because J is exclusive. So it can be equal to the length. And it's not a problem. Still fails. We were pointed at a right paren. But that's okay. Panicked at 2003. Okay. Let's use a simpler example. Where's a simpler example? Let's do start equals a dot get substatements, and then it's just vec a dot clone into iter dot collect. And let's do the same thing, but for a equals a, and then we should have a equals a dot clone, and then a. And then we should have, and we'll see how that goes. Okay. So we panic at what? 2004 again? Okay, so this one worked, but this one didn't. And where's the comparison? It's here. Let's pull these out. And, ooh. Okay, so the left side is the actual, the right side is the... No, I did that wrong. 0, 1, 2... Is this it? Nope. Slightly annoying to copy paste. There we go. Okay. Left and right. Trying to remember how to jump between parentheses. There we go. Okay, so that's all of the left. So this guy here is a binary symbol tree. Pop this out. Let's pop this out. And let's pop this out. So the question is, why are there 3? Why are there 3 of these? There should only be 2. Because there's this, and there's this. So what's different? This looks like it should be the same as this, but it's not. Why is it not? Because node trees is pointing at 2 different things. So here, left parenthesis 0, right parenthesis 0, node parenthesis 3, node trees is 3. Am I not filtering? I see the issue, sort of. So somewhere in get subtree, we aren't get left from range. Get range from left. So So it feels to me, so the thing I'm noticing is that this one and this one should be the same, but they're different because in node trees, one of these is just a 1, which is correct. One of these is a 3, which is incorrect. And this is where we construct it. It feels like we're doing these consistently. Subtree start, subtree end. Trees. That's what it's called. Okay, let's refine our test. What happens if we prior to doing this, what happens if we say assert equal a dot get child 1 and a dot clone. Substatement test. Fails at 2004. Okay. So this fails presumably for the same reason. No, left is none? What? Oh. Okay, so we're getting the second child of a equals a, which should be a. But I think this should fail because it should give me a subtree that's got a 3 in it. No. So get child passes, but get substatements fails. Okay. And actually, did we know that already? We might have already known that. Yeah, we already knew that. So what if we say subtree starting at, and then it's going to be what equals a 0, 1, 2, 3. we're expecting a failure on line 2004. We get a failure on 2005, so this passes. That's weird. Same issue though. Huh. It's subtree starting at I. It's literally what I'm doing in here. And is this right? Equals A 0, 1, 2, 3. What? Oh, I'm so confused. So confused. It's not a non-deterministic thing, is it? 2005. 2005 doesn't seem like it is. But I'm getting two different copies of A. One that looks like this, and one that looks like what? And one that looks like this. But all my function does is run through the arguments. It's on 0. Here's a question. What happens if I try to start the subtree at 1? So there is no okay, that's the problem. So actually actually, let's just do this. Left paren. And this can go away, right? I think this might be the issue. There we go. Okay. And get substatements and make another binary symbol tree methods. Okay. Get predicates. So predicates are sort of a specific thing which are used for arbitrary symbol nodes. Unclear if I need that yet. I think I'm gonna wait on that one. Get arbitrary nodes. These are all really cheap. Don't really care that much right now. Assume value is type. Sure. Get depth seems like a good one. Bits. So the point is we're just gonna say if self dot is left paren I max so far is equals 1. level plus equals 1 if level is greater than max so far, then max so far equals level. Else if self dot is right paren true level max equals 1 and then max so far. We return. Should be all right. Push child. It's a little tricky. Okay, things like this with child replaced. So these are the ones that we want to get a lot more efficient. Probably not quite that one. Get root. Get roots by name. So this is easy. Get roots by name. We just return nodes. Delimiters shouldn't be bad. Get node. Not sure that's what we want to do anymore. Okay, these ones replaced by name. So these should be really fast now. So here, replaced by name. This is just going to be self.nodes. Should be self-new, self.nodes. Let nodes be self.nodes dot clone dot into iter dot map label root if the label equals from, then to string to dot get name. Oh wait, this is worse than that though. This gets a little dicey. just test these as well. I think I need to add 1 to the depth. Yeah. This is why we test. Alright, I think I'm getting kind of tired. I'm hearing myself not speaking anymore, so I'm going to wrap up shortly. Thanks for watching. Let's make sure this test passes. Good. Okay. And I will catch you next time. Thanks, everybody.